Good morning, students. This is Dr. Sheikh Anwar from Department of Science and Humanities. Welcome to another session of this electrochemistry. In this session, we are going to take up a new topic called as saturated Calomel electrode. It is another kind of reference electrode which is used for potentiometric measurement. So, following are the contents. I will be talking about the SCE, that is the saturated Calomel electrode, followed by the construction of SCE. Then we will be dealing with the working of the SCE, and finally I will be classifying the SCE based on the normality of potassium chloride used, that is the electrolyte, and finally we are going to take up the advantages and limitations of SCE. From this video lecture, we are going to determine the electrode potential of any unknown electrode using SCE, that is the saturated Calomel electrode. And at the end of the day, we are going to understand the working principle of the saturated Calomel electrode as a reference electrode. Here we go. Coming to the first topic, that is the introduction of SCE, that is the saturated Calomel electrode. So before that, we have told that electrodes whose potential is utilized to measure or to find out the unknown potential is called as the reference electrode. And we have taken in the previous session the SCE as a reference electrode. In this session, we are going to use the saturated Calomel electrode as the reference electrode. This is the SCE electrode whose electrode potential is taken as 0.0 volts. And in this video lecture, we are going to talk about the another category of the reference electrode called as the secondary reference electrode, which is the SCE, that is also called as the Calomel electrode. And this Calomel electrode is another category of reference electrode. It is one of the category of metal insoluble salt electrode. Apart from this Calomel electrode, we can also have silver chloride electrode as a secondary reference electrode, and apart from these, we can also have quinhydrone electrode and glass electrode as other categories of secondary reference electrode. We should also know that a good reference electrode should have a stable and a well-defined electrode potential. So let us try to see whether the SCE or the saturated Calomel electrode will qualify the following parameter. What is the meaning of Calomel? Calomel is derived from the Greek word kalos and melos. Kalos means something which is beautiful, because this Calomel is nothing but a mineral salt of Hg2Cl2, which is very beautiful in color, and this Calomel on reaction with ammonia turns black. This Greek word melos refers to black, something black in color. So this Calomel is nothing but a solid paste of mercurious chloride, where mercury is in +1 oxygen state. And we are going to understand how this mercury and mercurious chloride as a combination is going to be an effective secondary reference electrode. And this, as I told very clearly, so it is one of the category of metal insoluble salt electrode, where the metal used is mercury, which is a liquid metal, and the insoluble salt of the metal is the solid paste of mercurious chloride, that is Calomel. Since we are using a combination of mercury and Calomel, we can also say this electrode as a Calomel electrode. There are other categories of metal insoluble salt electrode. This is one of the category, that is the Calomel electrode. The other category is silver chloride electrode. So this silver chloride electrode is also one of the category of metal insoluble salt electrode. This is a secondary reference electrode which is employed for electrode potential measurements. And this reference electrode has mercurious chloride and elemental mercury. This reference electrode is based on the reactions of elemental mercury and mercurious chloride. So we are going to see how this mercury is going to convert to mercurious chloride, and again mercurious chloride is going back to convert to mercury. And this electrode has potassium chloride as a saturated solution as the electrolyte. So we should understand that this calomel electrode has got mercury plus calomel and a saturated solution of potassium chloride, okay, as the electrolyte. And the whole setup actually is in a glass tube, and which is having a side arm which is nothing but a salt bridge. So this electrode is a reversible secondary reference electrode which can act as an anode as well as a cathode. This is the modern calomel electrode where we have got a glass tube, okay, and this glass tube is filled with mercury and mercurious chloride, that is calomel, and the whole setup actually is connected to a platinum wire, and you can see this can be connected to a external circuit, okay. And we can say that while representing the cell, we should write PT, comma, where mercury is in the liquid form, I can write HgL, followed by the calomel, which is a solid paste, which is written in S solid. So this is the potassium chloride which is used as a saturated solution, and these two lines represent the salt bridge. Okay, so based on the usage of the calomel electrode as an anode or a cathode, we can write actually the cell representation on the left side or towards the right side. And we should also know that we have used SCE electrode as a reference electrode. There we have used the following cell representation with platinum. This platinum foil connected to the platinum wire in SCE electrode, and the cell representation can be written as PT, comma, H2, okay, the 1 atmospheric gas which is bubbled actually in equilibrium with the H plus ions maintained at 1 molar concentration. Similarly, we have used actually a cell representation for the calomel electrode. Let us try to understand the construction of the SCE, that is the saturated calomel electrode. This calomel electrode can be easily constructed by a outer glass tube, and this outer glass tube is also having an inner glass tube, okay, and this inner glass tube can be filled with mercury in a liquid form, and above that we are having a solid paste of Hg2Cl2, that is the calomel, and the whole outer solution is filled with potassium chloride as a saturated solution. A platinum wire is been passed actually connecting the potassium chloride, the mercurious chloride, that is the calomel, and the mercury. Okay, this platinum wire actually is used as a external contact, okay, so that actually we can connect the other half cell, and we have got a side arm for opening of potassium chloride solution, and the whole setup can be enclosed with a plastic cap. Okay, so this is the way we can construct a calomel electrode using inner glass tube filled with mercury and mercurious chloride, as well as this potassium chloride solution. So we should know that this side arm can be used as a salt bridge, which is a source for maintaining electric neutrality, because we have seen in the previous lecture that salt bridge maintains electric neutrality by supplying the respective cations and anions. Finally, the cell representation is quite justified, where we have got a platinum wire, and this platinum wire is effectively connecting this mercury and mercurious chloride, okay, along with the potassium chloride, and this double lines represent the salt bridge. Let us try to understand the working principle of saturated calomel electrode. and we are going to see how this SCE can act as an anode or as a cathode when and when required. Let us try to understand. Suppose the SCE is used as an anode. Okay? So when it is used as an anode, I can write Hg liquid, comma Hg2Cl2 solid followed by KCl in aqueous and with a double line indicating the salt bridge. So we can have the other half cell as a on the right hand side. When it is acting as an anode, following are the reactions. So the elemental mercury is going to lose one electron. Here in this equation we can see two Hg atoms are going to lose 2 electrons and it is going to form Hg2 plus 2. Since it is an oxidation reaction, so we can see that the 2 electrons which are lost from the anodic compartment, they are taken in the cathodic compartment by the other half cell. The Hg2 plus 2 ions which are produced, they react with the Cl minus ions from the potassium chloride solution as an electrolyte to form Hg2Cl2. At the end of the day, on just nullifying these Hg2 plus 2 ions, I can write the resultant anodic reaction as 2Hg plus 2Cl minus will give Hg2Cl2 liberating 2 electrons. So we have seen the elemental mercury has lost 2 electrons and converted to calomel. We have told very clearly that this saturated calomel electrode is a reversible electrode which can act as an anode as well as a cathode. Here we see, when it is acting as a cathode, I just have to write the cell representation on the right hand side. Okay, so that actually this left hand side can be occupied by the other half cell which is acting as an anode. Suppose the other half cell is acting as an anode and our SCE is acting as a cathode. So this calomel is going to accept electrons. Let us try to understand. The Hg2Cl2 which contain Hg2 plus 2 ion. So we have got 2 mercurous ions and these mercurous ions are going to accept 2 electrons to form this elemental mercury, and the resultant reaction can be written as calomel accepting 2 electrons forming 2 Hg plus 2 Cl minus ions. If at all we carefully understand, okay, the cathodic reaction and anodic reaction are reversible. So I can say that the calomel can accept 2 electrons to form mercury, elemental mercury plus 2 Cl minus, or the other way around is that this mercury can liberate 2 electrons to form a calomel. This is the way we can say that the SCE is acting as a secondary reference electrode where elemental mercury is converted to mercurious chloride or mercurious chloride is converted back to mercury in a other process. Let us try to understand the SCE using Nernst equation. So we have seen in our previous lecture that the Nernst equation can be written by the formula E is equal to E naught, where E is the cell potential at a non-standard condition and E naught is the cell potential at a standard condition. 2.303 RT by NF log QC. And we also know that QC refers to the concentration of the product by concentration of the reactants. Here, since we have taken the reduction half cell, so on the product side we have got elemental mercury and chloride ions. On the left hand side we have got the calomel in the solid paste. I just have to write E is equal to E naught minus 2.303 RT by N. Here N refers to the number of electrons involved in the process. Since there are 2 electrons involved in the process, I can write N as 2 into F log. Since we are taking the concentration of metals and solids as 1, we can just take the concentration of Cl minus ions to the power of 2. Since we know that log A to the power of B is equal to B log A, I can just write the cell notation as E is equal to E naught minus 2.303 RT by 2F 2 log into Cl minus concentration. So this is going to nullify. At the end of the day, we just can say that E is equal to E naught minus 2.303 RT by F log Cl concentration. This is the way we can apply the Nernst equation to the SCE to find out the cell potential at a non-standard condition. So we have seen how this saturated Calomel electrode can be applied to find out the cell potential at non-standard condition by the simple formula, where E naught refers to the cell potential at standard condition whose value can be obtained from the electrochemical series table. So on substituting the R value as 8.314 with temperature 298 Kelvin and Faraday's constant value of 96500, we just end up with 0.0591 log to the concentration of Cl minus. This equation tells very clearly that the concentration of chloride minus ions plays an important role in cell potential. So finally, on substituting the value of 0.27 from the electrochemical series at standard condition, the final answer would be 0.27 minus 0.0591 log multiplied by the concentration of Cl minus. We can try to solve out some of the numerical problems using this equation, where we can find out the cell potential measurement at non-standard condition when we know the concentration of chloride ions. As we told clearly that from the Nernst equation, the concentration of the chloride ion is going to affect the electrode potential. Similarly, the temperature is also one of the factors which can affect the electrode potential. This is the table which defines very clearly how the temperature as well as the concentration is going to affect the electrode potential of SCE. Let us try to compare column 1 and column 4. As we see, the temperature keeps on increasing. The electrode potential value will decrease. So we can say that this temperature factor is playing a major role in the electrode potential of SCE. From 15 to 20 degrees, again to 25 to 30 and 35, this voltage is gradually dropping from 0.2511 to 0.2376 volts. As we increase the temperature, the electrode potential of saturated Calomel electrode will decrease. Let us try to understand the effect of concentration. We can see here that we have got two different concentration. One concentration of 0.1 potassium chloride solution and the other concentration of 3.5 potassium chloride concentration. So, as we increase the concentration from 0.1 to 3.5, the electrode potential value is decreasing. So, this tells very clearly that the chloride ion concentration will influence the electrode potential. So, we are supposed to understand two things. As we increase the temperature, the electrode potential value decreases. On increasing the concentration of chloride ions, the electrode potential value will also decrease. So, this table very clearly tells that as we increase the concentration from 0.1 molar to 3.5 molar potassium chloride solution, the electrode potential will definitely decrease. Depending on the concentration of potassium chloride used as electrolyte in SCE, we can have the electrode classification as saturated calomel electrode. We can also have the normal calomel electrode if the potassium chloride solution is of 1 normal. We can also have the decinormal calomel electrode if the potassium chloride concentration is 0.1 normal. Obviously, this concentration of potassium chloride will also influence the electrode potential. So, we can see here that as 1 normal potassium chloride is having 0.28 volts, the voltage obtained for 0.1 normal potassium chloride is 0.333 volts. So, the decinormal calomel electrode is having more electrode potential when compared to normal calomel electrode. Again, trying to reiterate that as we decrease the concentration from 1 normal to 0.1 normal, the electrode potential value is increasing. Universally, the saturated calomel electrode is the electrode which is used for measuring electrode potential measurements. This saturated calomel electrode having saturated potassium chloride as a electrolyte is used for determination of electrode potential with value 0.242 volts. Let us try to analyze the advantages present in saturated calomel electrode. This calomel electrode is very robust and it is one of the common electrodes used in corrosion studies. And this electrode is very easy to set up in comparison to SCE electrode, because we have seen in the SCE electrode maintaining 1 atmospheric hydrogen gas and 1 molar H plus concentration is very difficult. But here we do not find any of these problems in a saturated calomel electrode. And the potential of the electrodes remains constant even there is a partial evaporation of potassium chloride solution. And the results of the cell potential measurements are reproducible, which are the ideal characteristics for a reference electrode. And the cell potential measurements are stable over a long period of time in comparison to SCE electrode. The electrode is greatly affected by mercury, arsenic and sulfur. And whenever we use ions such as Fe+3, manganate ion, dichromate ion, we cannot use the SCE electrode. So, we do not have these kind of problems in saturated calomel electrode. And apart from the advantages, we have got some limitations of SCE. Since we told that the saturated calomel electrode is affected by the concentration of Cl minus. So, at high temperature above 80 degrees centigrade, the concentration of the Cl increases. Whenever there is an increase in the concentration of Cl minus ions, the electrode potential value will decrease. So, this is one of the drawback of saturated calomel electrode. So, apart from this, we should know that the mercury is of a greater health hazard. Okay? So, these two limitations actually will automatically pave way for a new reference electrode called as silver chloride electrode, whose potential is 0.22 volts. So, we should know that for a SCE electrode, the electrode potential measurement value is 0.0 volts. For saturated calomel electrode, the electrode potential at the standard condition is 0.244 volts. For silver chloride electrode, the electrode potential value is 0.222 volts. Finally, we have come to the end of the session, and we have taken the following points. So, we have taken this saturated calomel electrode as a reference electrode, okay, which can be used to find out the electrode potential of any unknown electrode. And based on the normality of potassium chloride solution use, we have classified the saturated calomel electrode as decinormal, normal, and SCE, saturated calomel electrode. And we have undertaken the construction and working of SCE, where it can act as an anode as well as a cathode. Finally, we have taken the advantages of saturated calomel electrode over SCE electrode, and we have highlighted some of the limitation of SCE. I hope you have understood this saturated calomel electrode as another category of reference electrode. If you got any doubts, you can email me or you can contact my number. So, thanks you once again for your kind attention. Take care.